First, let me thank the organizers for inviting me to this beautiful city and to this fantastic festival. I'm going to go back to very, very basic physics. You've heard of very high technology in the last talk, and we're going to go back to understanding gravity. And I'm going to do it historically, so I'll start where we all learned it, which is from Sir Isaac Newton. In 1680s, in 1687, he wrote a very important book called the Principia. And in that, he gave his universal theory of gravity, which I'll talk about in a second. But in addition to that, that's where he wrote down the scientific method, basically the way we all approach the science that we do. The theory of gravity that he did and worked on for many years is what we all learned in elementary school. He called it universal gravity because the way he understood it worked for everything that we knew of at that time and long after Newton's time to explain gravity. Whether it be the apple falling out of the tree, and the reason he called it universal is maybe it wasn't obvious at that time, but also the moon around the earth or the earth around the sun or anywhere else that we really have gravity in nature. And he wrote down a formula, which we learned, which described whether it was the apple falling out of the tree or not, that the force between two objects depends on the product of the masses of those two objects divided by the square of how far apart they are, with an unknown constant, which took another 100 years to determine what it was. And that was the universal theory of gravity. He had the sophistication to do the calculus, to say that the distance r in between was the center of gravity of those two objects. Anyway, that's where we started. That theory was fantastically successful and arguably the most important and successful theory of physics ever, even till now. So why did it have to be replaced? Or not replaced, but evolved? At the time Einstein came along, which is 200 and some years after Newton, there was only one possible place where Newton's theory didn't quite work. That was the orbit of the planet Mercury around the sun. Mercury is our planet that's the closest to the sun, and it has a very elliptical orbit, as shown in the picture here. And each time it goes around, it's influenced by the gravity of all the planets, the moons, and so forth in our solar system. And it comes back to a slightly different place. And you can calculate how far it would move, and there was about a 10% discrepancy. If you calculated, or anyone calculated, where it should come back, it was slightly wrong. And that was the only discrepancy with Newton's theory. However, even that could be explained possibly. And that is, in the 1800s, it was explained as possibly another missing planet, or objects, between Mercury and the sun. And you can completely make it work if there's some objects between Mercury and the sun. There were false discoveries in the 1800s, but by the time Einstein came, this was still unresolved. It actually was studied quite a bit later by NASA with very sophisticated satellites, and they determined that there was nothing larger than 10 kilometers between Mercury and the sun in a very sophisticated experiment. This was hardly a reason to develop a new theory of gravity. So it came about, as physics does, because we needed to have a little more sophistication in what we do with this very wonderful theory. And so it had some features that it couldn't explain, and I'll talk about those. Einstein then developed, I give his formula here, which I'm not going to describe. It's obviously more complicated than the one that Newton wrote, which is his theory of gravity, which was based on first taking the theory that had E equals mc squared that he had developed in 1905, the theory of relativity, what was called special relativity, and adding acceleration. That was velocities going very fast. If you add acceleration, you basically have gravity. And that's what he did. It took him 10 years to do that. And he developed a theory which basically has the feature, which I won't go into in any detail, but I'll show you the effect, that space and time are unified into a four-dimensional theory. So that's where Einstein came along. He made this theory, and that theory was first successful at what any new theory of physics should do. It explained and got the right answer for Mercury around the sun. So that's a success, but hardly the reason to throw away a theory that had been as successful as Newton's theory. Well, it had the feature that it also explained some problems that exist with Newton's theory, conceptual problems. The first one is that we all learned in school that if we jump up, our teacher told us, the earth pulls us down. Or the apple, when it falls down from the tree, is pulled by the earth. Or the moon is pulled by the earth, and so forth. But probably very few of you, not me, asked your teacher, what was it that pulled on you to pull you down to the earth when you jump up? Newton didn't explain that. And I don't know how many of you asked your teacher, but I didn't. In Einstein's case, what's illustrated in this picture is that by including space and time together, he gets the fancy words that you hear, warpage of space-time. In this picture, you see the effect by having a grid, which is a coordinate system, which can be thought of as a trampoline, say, and a massive object on it distorts the space around it. And that's the key to why an object is attracted. So if an object is out here, it rolls down the hill toward the object here, the Earth. So the apple falls down the incline. Or the moon, when it's going around, stays at the same level and goes around. So the effect of why the Earth pulls, and there had been many explanations, usually involving falsely electricity and magnetism, to try to explain what pulls in gravity before Einstein came along. So that's a success of this new theory. The second problem that Einstein realized, and Newton also actually realized or alluded to, is that when the apple falls from the tree, or when anything happens at a distance, the effect in Newton's theory you sense immediately. So if the apple falls out of the tree and you see it immediately, that's fine, and that was Newton's theory. But if, in this picture here, the sun were to disappear right now, it would take 8 minutes for us to know about it, because that's the time it takes the light or the signal to travel from the sun to the earth, 8 minutes. It's inconceivable that somehow gravity would have an effect that comes immediately. So in Einstein's theory, there's one speed. We call it the speed of light, but it's also the speed of the gravitational signal, and it's the speed of light, and it takes 8 minutes. So this is basically fixing what, in words, Newton's theory had, which is instantaneous action at a distance. And so these two conceptual features were the improvements that basically come about by having Einstein's theory of gravity. That's all fine, but generally, to accept a new theory, even if it isn't as monumental as replacing Newton's theory, we basically have to propose or predict something new. And what he did is predict the bending of light and exactly how much it would bend. If light goes near a massive object, and in this picture, light goes near a massive object, which is the sun, and the earth, if behind the sun, light is coming and grazing the sun. We can't see that normally, but if we picked a time when the sun is black, meaning an eclipse, we can maybe trace that. And that's exactly what was done to see that light actually does bend as it goes around the sun, and that was done by Sir Arthur Eddington. And that actual observation, which was done 4 years after Einstein's theory of general relativity was introduced, was basically what made Einstein famous to the world. It was in all the newspapers and basically made him a household name. To physicists, he was a household name for us in 1905 when he solved 3 or 4 of the most important problems in physics, each more or less with a month separation between them. So basically, this is what made him famous publicly. And then what happens, a little bit like the last talk, only maybe the beginning, is once you discover something new, you usually can make use of it if it's a physical principle. In this case, the fact that there's bending of light, which we use to prove that Einstein's theory can calculate the bending of light in this phenomenon, we actually use it now. So for example, astronomers use it in order to see and study an object, a source, when it goes past a known object and light bends, so we can see something about an object. Because of that, we call it gravitational lensing. There's an example of a lit object doing that, and the most famous one for people to see is called the Einstein cross, where there's an object behind is seen as these bright lights afterwards. There's also a very practical use for general relativity. So once we learn something in physics, even as obscure as Einstein's general relativity, it turns out to be useful. In this case, fantastically useful, because almost all of us find our way around these days using GPS. But GPS actually only works because of general relativity. And in fact, it was developed by the military, and it was hard to convince them that they had to incorporate general relativity to get the right answer. So the scheme for GPS is that there's 24 satellites in the original scheme around the world going rather rapidly and at high altitude. They're going at about 14,000 kilometers an hour. That's fast enough so that in Einstein's terms, they're relativistic. If they're relativistic, we have a saying when we teach relativity that moving clocks tick more slowly. And in fact, if you look at the correction for a day, the amount that the clocks tick more slowly it doesn't seem like much, but it matters, as I'll show you, in determining where somebody is, of about 7 microseconds per day. General relativity, which is this new theory, also matters. And the reason why is the satellites are high enough so that the gravitational field is only about a quarter of what it is here on Earth. If it's only a quarter, then we have to make a correction also for general relativity in these satellites. And that correction is bigger than the one from special relativity. And when both of them are made, there's a correction of 38 microseconds per day. That correction is made in electronics in each one of these satellites. And so we never see it. But as I said, if it wasn't for our knowledge of general relativity, we couldn't make GPS work like it works today. And in fact, if this number seems very small, if you actually try to determine what it means, if you actually think of a road as, say, 10 meters wide, a pretty wide road, how long would it take before you would be off the road? If you did not make this correction, it's about a minute or two. So that's general relativity itself, a new theory of gravity. Einstein, in 1916, 1 year after he introduced the theory of general relativity, realized something else. And that is when he looked at the equations, which I won't do for you, of general relativity, and set them up in a particular way, to him, they looked a lot like the equations of electricity and magnetism. In fact, they looked so similar that he didn't derive anything from basic principles, just from the fact that he could set up the formulas and they looked pretty much alike. Being Einstein, he made the leap that since in electricity and magnetism, we also have electromagnetic waves, which we use all the time, including the lights in this room, then gravity, since it has the same form, must also have gravitational waves. Not derived from basic principles. He wanted to do that, but didn't know how. That first paper, which was very short and made this prediction, also had a bunch of errors in it. But 2 years later, he wrote a second paper, and in that paper, he fixed the errors. Being Einstein, he didn't admit there were any errors. He just did them right the second time. And in the second paper, he did something else that was very important. He explained what the source would be of gravitational waves. So in electromagnetic waves, we learned that they existed after we knew about electricity, we knew about magnetism, by a physicist named Hertz. And what he did is go into a laboratory and create electromagnetic waves. He did that by taking two charges and oscillating them like this, and going into the next room. And when he did that, this made electromagnetic waves. He detected them, and then he moved his detector forward and backwards and saw that it was wave-like. And that was a beautiful experiment that showed that electromagnetic waves exist. Of course, now we use electromagnetic waves in everything, radio, microwaves, light, and so forth and so on. But that was the beginning. In this case, what Einstein showed is for gravity, it's not a dipole, but four poles. And to make four poles, you do something like I'll show in a minute. So first, he showed that there would be gravitational waves, and this is the kind of source that we've detected that I'll show you. If you have two objects going around each other like this, they'll make this quadrupole motion and make gravitational waves. The problem is that the waves have to be strong enough and the ability to detect them sensitive enough, which I'll come to, so that we can see gravitational waves. But that's the source, what it looks like. And those waves going out are the waves symbolically like gravitational waves. This theory that there were gravitational waves by Einstein didn't really go very far. He didn't derive it from first principles. And during the same era, quantum mechanics emerged. So most theoretical physicists worked on quantum mechanics, not general relativity, this complicated theory of gravity. And the problem of whether there are gravitational waves didn't have very much traction in 1915, 1916, and 1918. Einstein returned to the problem after he immigrated to the US in the 1930s, along with his colleague Nathan Rosen, and they tried to develop the theory of gravitational waves from the fundamental principles of general relativity. And they submitted a paper where they weren't sure that there were gravitational waves. They basically developed calculationally some infinities, which is a problem that you have if you don't do things quite right. Got worried that maybe they didn't exist. So it was even a question for Einstein in the 1930s. He finally wrote a paper that did have gravitational waves, but it really wasn't a proof. It wasn't until the 1950s, after Einstein died, he died in the early 50s, that there was a meeting which most people point to as the time when gravitational waves were first really believed as something real. And that was a meeting of the leaders in general relativity, the theory of gravity in the world, that came together in the US in a place called Chapel Hill, North Carolina. And that meeting had about 50 theoretical physicists, and a theoretical physicist named Pirani made a beautiful development from first principles of gravitational waves as the opening talk in the meeting, and that was good. My colleague at Caltech, Richard Feynman, was at that meeting, and he, in his characteristic manner, said that if gravitational waves exist, they have to be able to transfer energy. So how do you say, Otherwise, they're just not a real thing. So how do you test whether it would transfer energy? He made what we call a Gedanken experiment, a thought experiment, a bar with rings on it, and then a gravitational wave goes through. If a gravitational wave goes through, it expands the bar and contracts the bar at the frequency of the gravitational wave. That creates some friction on the rings. They move a little bit, but friction is...
Txikiagotu egingo da eta frikzioa usaietan ikusiko da. Mugimendu pixka bat egongo da, eragingo du, baina batik bate frikzioa da garrantzitsua.
Que después amplió
Piranik landu zuen teoria hori, horri esker, zientzialarien komunitateak aitortu zuen, existitzen zirela gravitazional horiek. Baina, evidentzia horiek oraindik oso ahulak ziren erabate frogatu alizateko. Eta detekzio maila zergatik zein hain ahula. Oso zaila ziren antzematen detektatzen. Neurri batean natura horretatik ahula delako. Hasieran dispertsioaz hitz egin dugu, denboran eta espazioan gertatzen den dispertsioaz, han oso argia zen marrazkia esageratuta zegoelako. Baina dispertsio hori gertatzen da, baina oso modu zurrunean naturaren baitan. Distortzio hori oso txikia da, eta beraz naturak zain jartzen digu hori frogatzea. Esperimentu hori ondoren, halako batean, esan zuten, baietz, egongo zirela, baina hori esperimentu batean behatzeko moduko zerbait izango zela, benetan frogatzeko. Aluminiozko barra bate erabiltzen zen, eta hor gravitazionalak baldin bazuen zabaltze bat egon beharko zuen eta murrizte bat ere bai, konferentzia aurreko biltzarrean ikusi zen bezala. Weber ere biltzar horretan zegoen, eta esperimentu berberak egin zituen hark ere. Zein da horren efektua, ondorioa? Ze efektu daukate beraz gravitazional horiek?
And squashes
zabaldu eta zurrundu egiten du denbora espazioa. Eta uinaren zabalera dago iturriaren indarraren baitan, horren menpe. Eta guk iturri oso indartsu bat detektatu genuen. 10 ken hogeita bat. Hori da espresioa. Beraz oso zenbaki txikia da eta nontzen oso zaila da. Hori da uinaren zabalera. Eta nik distantzia bat baldin badaukat, tarte bat baldin badaukat, hori aldatuko da proportzio horretan. 10⁻⁻⁻⁻. Hori guztia barra horretatik uin gravitazionala pasatzen da. Edo beste da batera salduta. Hemen ustai badaukat masa zu dituenak eta zirkulo pasatzen. Eta hortik zen baldin bada uin gravitazional bat pixka bat aldatu egingo da daukan forma hori. Jada ez da zirkulo bat izango eliptiko bihurtuko da. Baina aldaketa hori lehen aipatu dugun horren tamainakoa da. 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻
txikia izanik,
hicimos un experimento mucho más grande que un metro, por supuesto.
Esperimentu asko handiago bat egin genuen, metro bateko baina asko handiagoa aldaketa hori detektatu alizateko. Errazagoa izan zedin. Kilometro ari gara eta ez metro. Baina esperimentu horretaz itzen.
¿Por qué no podemos hacer el mismo experimento?
Logika dezagun zergatik ezin genuen jertzen pareko esperimentu bat egin.
laboratorio y quiero hacer este
Nik laboratorio bat daukat eta esperimentu bat nahi dut.
Físicos experimentales que
Eta
enseñaron
fizikari esperimental gisa esan zuten aldagai guztiok kontrolatzen behar dituen, bestela akatsak emango zituen maitzak.
tener una fuente que
Beraz,
entendemos
jertzek
y
bezala,
la capacidad de comprobarlo todo.
iturri bat behar genuen, hartzaile bat behar genuen, eta dara ulertzeko gaitasuna behar genuen. Baina hori ez da posible, zenik laboratorioan esperimentu bat egiten baldin badut, eta tutu hori hartzen baldin badut, bi zirkulo horiek bola horiek dituenak, alde banatan, eta hori biratzen baldin badut, birarazten badut, orduan uin gravitazionalak sortuko ditut. Baina, erreparable zaigun zifra hori zenbaki hauek. Alde bakoitzean 1000 kiloko pisu parte jarriko dut, eta segundoko 1000 bider biraraziko dut.
Y solo me voy a 300 metros.
Laboratoriotik 300 metrora joango naiz, baina oraindik gertu ez naiz jartu zen. Zifra hauek oso exageratuak dira, baina hala ere, proportzioa ez da amar ber minus hogeita bat, ez da amar ber hogeita amar izango litzateke. Beraz, zifra hauekin ere ez gara gai izango uin gravitazionalak antzemateko aldaketa oraindik ere oso txikia da. Beraz, natura jo behar dugu. Eta natura ere oso interesantzia. Naturak baditu bi objektu elkarri bueltaka dabiltzana. Karren biran dabiltzanak, zulo beltzez ari gara.
But if I put in the numbers for what we did observe, each one of them is 30 times heavier than our sun.
Estamos hablando de cada masa que pesa 30 veces más
bakoitzak gure eguzkiak alako hogeita marko pisua dauka, eta distantziak garagarriak dira. Eta hor bai, zifra egokia lortu nahi dezakegu amar ber minus hogeita bat, ikusi nahi dugun, lobeatu nahi dugun beraz. Eta nola egin, bada teknika bat oso sentibera dena, interferometria dena. Zer egiten interferometro batek? Distantzia, tartea, neurtzen du bi norabide ezberdinena. Ura argia hartzen du eta bi norabideetan hartzen du, gero ispilu batera bazen du, talka egiten du, eta distantzia berbera baldin bada, bueltakoan hori ezer esan geratzen da. Izpiak ezer esan geratzen dira. Hemen ez da seinalerik sortzen. Atzailera ez da ezten. Baina besoietako bat pitin bat luzeagoa bada, bestea baino orduan bai, seinal bat sortzen da. Eta hori da interferometriaren teknika. Modu simplean, baina hori da egiten duzuna. Zehaztasunari dagokionez, ikaragarria behar du izan, eta hor dago sekretua, esperimentuaren sekretua. Hau da ilustratzeko modu bat, irudikatzeko modu bat. Ez dakit inoiz interferometro bat erabili duzuen, edo fizika ikasi bat imaduzue, bat ziurrenik erabiliko zenuten. Interferometro bat emitartez, saiatzen gara gertzak ikusten, edo argiaren uin luzera ikusten saiatzen gara. Eta laboratorioan, gutxiago edo gehiago, zehaztasun, presizio, maila, kalkulatu dezakegu, interferentziaren 10 bat gara. Gero beste laboratorioetan, milako parte bat detektatu dezakete, eta gu detektatu bat eguna, 10 ber minus hogeita bateko zehaztasun hori lortu behar dugu. Beraz, edo zer interferometro baino zehatzago sentiberago izan behar du, behar dugun tresna. Tira, asko egin genuen, trikimailu asko erabili genituen, interferometro hori lortzeko. Zertarako, aldaketa hain txiki hori neurtzeko. Bigarren arazo bat ere bagenuen, asko detaila zen gainera, arrunta dirudi, baina ez da.
Vamos andando, pues parece que la tierra es algo estable.
Badirudi lurra leku egonkor bat dela, baina ez da. Gure planeta mugitu egiten da, izugarri mugitzen da. Eta oso zaila da lurra egonkor. Beraz, tresna hori hartu behar genuen, eta flotatzen jarri behar dugu.
lo tenemos que hacer también a una
eta hori nola egin behar dugu? Proportzio berean, 10 ber minus 21 proportzio horretan. Beraz, edozen vibrazio ez gaitu horretara
movimiento muy pequeño, de 10 a la menos 12,
oso txiki bat baldin badago, interferentzia sortuko dira.
Un problema muy difícil de resolver.
Eta hori konpontzea oso zaila izan zen. Eta nola lortu genuen?
La Fundación Nacional de la Ciencia en los Estados Unidos.
Zientziaren Fundazio Nazionalera jo genuen, Estatu Batuetan, eta gure esperimentuaren berri eman genien, esan genien, teknologia batzuk garatu behar dituela, eta pixkanaka finanziazioa eskaini zuten. Kaltekekoa zen taldea, haitikoa. Ez zuten nahi bi talde bakoitza bere aldetik lan egitea, eta orduan, pixka bat lotura, behartu xamar bat sortu zen, baina jarraitu genuen elkarrekin lan egiten, ondo moldatu ginen, eta gure proposamena eraman genuen esan bezala eta onartu zen, finanziazioa eman zuten. Baina Kaliforniako kokapena aukeratu beharran eta Maingo beste bat,
And we ended up with some politicians.
Hemen ikusten dituzue biak, alabiak.
So we have two detectors, and they're separated by
3,000 kilometers.
Hasi ginen, ez da bat aiparraldean bestea egualdean zegoen, eta 3,000 kilometro zuen bien artean. Argiak milisegundoak behar ditu, distantzia hori egiteko, hemen dator, argia ikusten zuen, nola joisten den, 10 milisegundo behar ditu, iparretik egoaldera egiteko, kontrako nola bidean ere, 10 milisegundo behar ditu.
Pues llegar al mismo momento arriba. Entonces, cada señal tiene que estar dentro de
bakoitza
un rango de 10 milisegundos.
10 milisegundoko tarte batean egon behar du elkarren gandik. Alegia, bi detektagailu dauzkagu, biak ere nahikoa sentibera dira, alde txiki hori detektatzen. Bueno, gero esango dizuen nola lortu genuen lurretik isolatzea. Hoiek dira bi kokapenak, arbolak ikusten dituzuen, Luisianako kokapena da, eskuinekoa eta ezkerrekoa berriz basamartuaren erdian dagoen leku bat da. Bilekuak ezberdinak dira, baina gu lurretik isolatu ginen, eta orduan etzitzaiona jola benetan bilekuak hain ezberdinak izatea. Hemen ekipamendu ikusten zuen, zure asko daude hor barruan eta tresna ezberdinak dauzkagu deposito horietan. Azpiegitura oso zehatzatzen, oso berezia zen, ze azpiegitura berbera erabelik nahi genuen esperimentu osoan zehar. Azpiegitura hori oso garestia da, eta pixkanaka tresna garatzen zijoazen, baina azpiegitura etzen aldatzen, espiluak dauzkagu, eta hemen dago giltzarria. Nola lortu genuen isolatzea. Lurraren parte batean 10 ber minus 21 proportzio horretan. Hor dago gure arrakastaren gakoa. Urteak behar izan genituen hori erabakitzeko nola lortu lurretik isolatzea, baina erantzuna azkenean irtenbidean nahiko sinplea da. Azteko, pentsatu behar dugu, adibidez, autoz guazenean, amortiguadorea dauzkagu, bestela oso deseroso, ez amortiguadorik gabe. Zer egiten du amortiguadore horrek? Frekuentzia aldatu egiten du zuloak sentitu ez ditzagun, gu frekuentzia altu batean lan egiten dugu, baina vibrazioak frekuentzia horiek altuak izatetik txikiak izatera pasatu nahi genuen. Autoarenak baina baino frekuentzia asko zondiagoa ziren, nola ez, eta horrelako amortiguadore bat diseinatu genuen, baina inoiz ez ginen iritsi gure behar genuen neuzira, 10-bira, baina beste teknika bat ere garatu genuen, osagarria izango zena.
Reventamos la rueda, copiamos.
Noski, ez genuen gurpila asmatu, beste ideia bat kopiatu genuen. Adibidez, hegazkin batera igo eta kasko batzuk erabiltzen ditugunean, edo tapoi batzuk hobeto izan da, bai, tapoi batzuk erabiltzakegu motorraren zaharata baina azapataren ahotsa entzun ditzakegu, beraz, isolatu egiten gaitu motorren zarata horretatik, ez? Baina zarata jakin horretatik besterik ez. Zerbait esango eta haren ahotsa entzuteko gai izango da. Tira, guk ideia horixe bera hartu genuen. Ostu genuen, eta erabaki genuen horrekin zerbait aktiboa sortzea, gai izango zera mugimendu hori, lurraren mugimendua kaptatzeko
una serie
gai izango zena, baina gero desagertatzen egingo zuena. Beraz, amortiguadore sismikoak garatu genituen. Eta horiek gai ziren mugimendu guztia antzemateko. Eta mugimendu hori bertan bera edo desagertatzeko. Eta teknika horiek erabiliz neurketa egiteko gai izan ginen. Eta zer ikusi genuen hori guztia martxan jarri. Bi zulo beltzen fusioa bateratzea. Hemen dauzkagu, bi horiek.
Simulation, but a computer rendition of the actual data that we took.
Eta Nikola irakutsiko dizuedana da gure datuen interpretazio bat. Ordenagailu batek egindako interpretazioa, ez da artistikoa, informatikoa baizik.
It's a mathematical concept.
Zer da zulo beltz
But
bat?
it's also a
Es
physical
un concepto
concept.
matemático, pero también
Kontzeptu matematiko bat da, baina baita fisikoa ere.
Nothing can get out.
es tan fuerte que no
Gravitatea
se puede
hain
escapar a nada.
handia da, ezerk ezin duela bertatik alde egin.
It has gravity,
Sol,
it's
bueno, la
pulling.
Tierra,
Que
Of course, everything
lurra daukat eta eguzkia daukat, eta biek gravitatea daukate, baina gauza batzuk
Nothing can get out.
alde egiten
Light
dute.
bends, so even light can't get
Baina,
out if it's strong enough.
baldin daukat zerbait hain dena trinkoa eta argiak ere alde egin ezin badezake, orduan zulo beltz bat
campo gravitacional, eso es un agujero.
eremu gravitazional horretatik atera ezin baldin badu ezer, orduan
Más pesado.
zulo beltz bat da.
It could be strong enough.
Gure guztia baina 3 aldiz astunagoa da eta horregatik sortzen du eremu gravitazional hain sendoa edo hain handia. Izar guztiek
Light elements first, hydrogen, helium.
erre egin behar du
Eventually it gets up to about
hidrógeno,
iron,
helio, etcétera.
and the fusion
Luego
process
ya
doesn't
empiezan
work.
a
Erregaia.
otros elementos, la fusión ya no funciona.
Osagai batzuk lehenbizi, gero beste batzuk, galako batean
Actúa en algún momento la gravedad
hori bukatzen denean gravitateak
colapsa del Sol, eso es una supernova.
gravitateak irabazten du eta hor kolapso bat gertatzen da eta hori supernova da, baina gure eguzkiaren masa 3 aldiz baldin bada, orduan bai
Y a veces en la
zulo beltz bat
tenemos
daukagu,
dos.
hori daukagu hemen pantailan. Eta naturan olako bi dauzkagu,
Tierra,
Is something
dos
that is
agujeros
ilargia,
que están muy cerca.
lurra,
Y aquí,
eguzkia, lurra eta bar.
dos agujeros.
Eta hemen hori ikusten dugu, bi
energy and gravitational.
zulo beltz, elkarren biran, energia igortzen ari dira, uin gravitazionalak ere bai, eta pixkanaka bat egiten ari dira.
We saw the last two
Espiral
tests.
moduko batean elkartzen ari dira.
Nosotros solo vimos
And as they're merging in,
las
they're
últimas
affecting all
2
the
décimas
galaxies.
partes de un segundo.
Segundo baten azken bi parte besterik ez ditu ikusi, eta horrek inguruko galaxia guztiei eragiten diete, eta halako batean zulo beltz bakar bat sortzen dute. Hori ikusi genuen ez Newtonen, ez Einsteinen garaian, baizik eta 1,3 milioi urte atzera eginda, baina gugana iristeko seinale horrek demorari guztia behar izan du. Luisiana eta Washingtonen ikusi ahal
Look at a
izateko.
local map. So this local map I
Aquí vemos un mapa local.
Hemengo mapa bat dago, ezta? Euskal Herrikoa,
and
Donostia ikusten
if
dugu,
I
eta
superpose this
Bilbo
on
ere bai.
top, superpongo esta imagen.
Nik irudioi gain jartzen bat esnaduz, horrekoarekin, bi zulo beltzena, elkartu aurretik, hortarte badago, distantzia badago, bien artean, bi hirien arteko distantzia bera da, eta zulo beltz, koitzaren pisua da, horraren 10 milioi alako masa dauka. Eta espazio horretan, biraka ari dira, argiaren abiaduraren erdia, abiadurari duri, baina hori da abiatu genuena, ikusi genuena. Eta elkartzen dihoazen neurrian, energiaren euneko post, uin gravitazionalen moduan igortzen da. Esan bezala, 1.200 milioi urte atzera gertatu zen, eta hori guztiak espazioan edatzen dira eta lurrera iristen dira. Exageratzen dira, baina horrelako distorsio bat sortzen da. Eta horrela bai gai gara uin gravitazionalak detektatzeko. Exagerazio bada, lurra ez da hainbeste, baina guk tresna batzuk sortu genituen, eraiki genituen, uin horiek detektatzeko. Zer gertatu zen?
300 millones de años.
Es que milioi urte gero, hor ikusi genuen inguru bat, ego hemisferioan, nola platano moduko forma daukan hori, hortik pasatu zen uina, eta angelu honekin iritsi zen, eta guk une hori erreplikatu egin dugu hori esateko. Guk Luisianan ikusi genuen seinale hori, eta horietira datu gordinak, ez ditugu aldatu, ez ditugu landu, horietira ikusi genuen datuak.
That was the time it took from when they were apart.
Etzanean daukagu denbora segundoetan eta vertikalean 10 minus 21 eskema hori daukagu.
Milisegundos y podemos ver que estas oscilaciones se van
creciendo. Zen nolako oszilazio dauden, nola dihoazen aldatzen, gero eta alde handiagoa dago, tontorra handiagoak eta jetxiera handiagoak baita ere. 10 milisegundu geroago seinale berbera ikusi genuen Washingtonen. Eta hau da evidentzia, hau da froga. Horri esker dakigu uin gravitazionalak egon bat direla. Eta hau da egiazko behaketa. Hemen ez da oso ondo ikusten, zein da aurre ikuspena, baina lerro oso fin bat dago Einsteinen ekuazioetatik egin da aurre ikuspena.
Basado en la teoría de la general,
erlatibitatearen teoria orokorrean oinarrituta, ia berbera da, berdina da, guk behatutako datu ia berdina.
Desde entonces hemos observado
arrezkero 10 evento aztertu ditugu oroar eta beran eskuinean 2 minutu iratzen evento bat izan genuen.
Es otro tipo
milisegundotan. Evento mota hori
demuestra
que
hemos comenzado a poder
hasi garela behintzat gauza desberdinak ikusten espazioan. Hor ikusten da bi neutroi izarren talka, ez dira zulo beltzak eta horrela talka horretatik ere talka hori ere behatu dezakete astronomoek ez bakarrik fisikariek. Beraz, orain hasi gara zientzia egiten gravitazionaletan oinarrituta. Naturak jadanik ez ditu bakarrik mugatzen. Orain behaketa precisoak egin ditzakegu oso doiak.
Os muestro cómo podemos mejorar la
dezakegun doitasuna 10 faktore batean. Hemen Einsteinen teleskopioa hemen dago, Europan, lurpean, triangeluan dago, hori guztiari esker asko zere sentiberagoa da. Baina mezu nagusia da, teleskopioak lehen oraingoak baina asko zere kaskarragoa ziren, eta oraingo behar direnez, hobetu egingo dugu, naturak ez gaitu jadanik mugatzen
nuestra
gaituen
capacidad de fabricar buenos
da
instrumentos.
tresna onak egiteko
En el futuro,
etorkizunean
vamos a poder diseñar
diseinatuak izango
nos
ditugu
van a permitir ver estos eventos, esos
tresnak eta
agujeros negros que están en el borde del universo, que están ahí donde nos llega la señal
eta
desde
seinala
los principios
seinalea
del tiempo, con lo cual vamos a
iristen zeu
poder
gainera
jugar al Big
denboren
Bang,
hasieratik beraz Big Bangea itxiko gara unibertsuaren lehen momentuaren itxiko gara ikusteko nola bilakatu den gure unibertsoa.
¿Qué va a ocurrir entonces?
Eta ze gertatuko da orduan uhin elektromagnetikoei esker azter dezakegu astronomia mikrouhinekin, hainbat uhin frekuentzia eta azken ere honetan ugarri batzuk esan ditugu eta lagundu egin digute aztertzen hainbat ikuspegitatik. Gauza bera gertatuko da seguruenez uhin gravitazionalekin begiratu. Orain lan egiten audio bandan. Hori da gure egungo banda. Gaur egun baditugu esperimentuak, ez bakarrik espazioan egin hor aztertu ahal izango ditugu beste batzuk ópticas, uhin optikoak, edo aurrerago frekuentzia apalagoetan. Eta pulsar deituetakoetan surtzen ari direnak bat taldetan. Ez da egun batetik bestera gertatuko hori egia da, denbora bat beharko dugu, baina azkenean gogoratu dezagun nola hasi zen astronomia. Dena hasi zen Galileorekin, bere lenteekin esker, hasiera batean betaurrekoetarako erabiltzen, aurrera lehen ziren eta Júpiter ikusi zuen, eta gero Júpiterren
And that was the beginning of
las
astronomy.
principales,
This is now 400 years
eso
later.
fueron
Astronomy has developed
horiek esan ziren
powerful
astronomiaren
instruments.
astapenak.
We've learned a huge amount
Eta
about
hori esker
fueron desarrollando los
astronomy.
garatu
instrumentos
joan ziren tresna astronomikoak
We're at this very beginning stage
unibertsuaz, erradiazio elektromagnetikoa eta horrek lagundu zuen geroago uhin gravitazionalak proposatzen. Hor ez gara elektromagnetismoa zari, baizik eta beste
diffuse electromagnetic radiation that we see. We don't know what the rest is.
unibertsuan dauden gorputzen
So it's almost certain that having a very different
uhin
kind
mota
of
hori
even the black holes, we
beraz,
saw that
nahiko
yesterday.
konbentzituta
We're going to show a lot more
egingo direla tresna zerriak eta lagunduko digutela unibertsitatea hau ezagutzen. Eta oraingoan ez du lau mende beharko. Nik uste dut asko